Hello, I'm Simon James Lewis, but you probably figured that out by now. What I kind of would really like to be talking about this evening is Bristol Hemp-lime. I'm inundated with people that want to know more about this stuff that I'm doing, and because it seems to be solving the problem, but without any of the unintended consequences that none of us are enjoying. However, I don't have the resources to really cope with the number of inquiries that I'm getting for this. So I brought you all here today, and we're going to have a discussion. And I really look forward to introducing you all after I've presented a few ideas, and we can have a drink and etc. Get to know each other a bit more. So Bristol Hemp-lime. Hello, Ben.
Just in time.
You're nearly. Is basically putting hemp-lime, which is a new build construction technique. Ian behind us there can tell us more about the shopping malls that are being built with hemp-lime. But I'm just putting little bits to solve damp problems. Yale. So we do have a few householders here that have already done this, and there's also a few people here that are interested in doing it, and there's lots more people. So trying to get them together and create a kind of teaching, learning process. Yale has tackled a difficult north-facing facade of a Victorian terraced house. And Nick, who, well, this is his first condensation-proof bathroom, and he's currently working on his second one. But we'll see that later. There's Nick putting his wallpaper up, linen wallpaper, of course. And that there is a condensation-proof bathroom built with hemp-lime. Right. This is what I'm actually here to talk about this evening. This is what you came for. I'm going to talk about energy retrofitting, why it doesn't work and why it causes damp. A little contentious, especially with you lot. Right, and we're also going to have a look at hygrothermal passive heat recovery, understanding the relationship between energy and damp. This sounds really, really complicated, and it's not. It's really, really simple. I've got a really, really simple model that I use when I go in solving damp problems, and I'd like to share it. And finally, architectural detailing. This is what I want to do my PhD on. I want to go and look at this stuff and actually figure it all out, because I've got this model that works and I want to explain some stuff. So it's going to be a bit tricky, that part, so bear with me. Right, we're going to begin. Energy retrofitting. The cost versus savings are upside down. I'm wearing the same clothes I was wearing last year. It's getting worse, isn't it?
Too much detail.
Makes sense. The vapour gradients are inside out. Laundry day. And the EPC model is back to front. We need to fix that. Maybe stitch it up. Right, upside down. This is my energy performance certificate. It qualifies me for a £10,000 loan to have wall insulation fitted on my house. This is predicted to save me £140 a year and take 70 years to pay back. Actually, it turns out it's actually going to underperform. It's going to actually save me £70 a year, and you don't need to be a mathematician, Pete, to work out that's going to take 140 years to pay back. And that doesn't even consider the fact that it's a 7% loan or whatever it is, and that's £700 a year. Why on earth would you want to do this? Oh, and it causes damp. That's funny, because the stuff I do solves damp. This is why. What we've done to our homes is unbelievable. We filled our homes with vinyl paint and cement renders, and we've taken away the traditional thermal envelope. We've also installed gas fires, and we've gone open plan and gone for that kind of California living, and it's causing chaos. But none of this is understood from an energy retrofitting model that is based on new building science, not an understanding of traditional architecture, as well as how people actually live in their homes. If what we've been doing inside is bad enough, what we've been doing outside is terrible. The cement rendering, again, you get a bit of a damp problem, or we'll paint that, whether it be inside or out, it's causing chaos. So that's my EPC. Next. The vapour gradients are inside out. Here is a traditional thermal envelope. It's hygroscopic, we'll come on to that. And we're going to insulate it. The problem is, we insulate it on the inside, we get a vapour gradient problem. So for those that aren't familiar, very simple model. I know there's people in the room that could do a much better model than this, but still. The model is static. It predicts that it's going to be 20 degrees inside and it's going to be 0 degrees outside. and the relative humidity inside is going to be high and it's going to be low outside, actually it's going up and down all the time. So the model doesn't actually understand the fact that it's changing. And we've got things like thermal inertia and hygroscopicity. So if we insulate on the inside, we have to put a vapor barrier in order to stop these lines crossing, because when the streams cross, you know, there's marshmallows flying everywhere. So the problem with doing this is we then end up with this vapor barrier on the inside, and actually it's all the vinyl, paint and cement render and all those things we're trying to get, well, I'm trying to get out of the building to solve the damp problem. So instead of fixing the damp problem, the interstitial one, we end up creating this massive moisture problem within the home. So the solution is to put the insulation on the outside. That makes sense, doesn't it? You keep the wall warm and then we don't have a damp problem. However, this causes various problems. It's costly, it's complicated, and it's unsympathetic. Fundamentally, it's just not appropriate for our conservation housing stock, let alone our average Victorian terraced house. And we'll come to that. So what I'm doing is I'm putting a breathable insulation on the inside, which apparently breaks all the rules, and you can't do it. And what this does is it captures both the temperature and then allows it to radiate back. And it does this by bringing the moisture in and allowing it to go in. So of course moisture can move through here, and this can all go up and down. This is buffering. And actually there's stuff going on the outside of our traditional architecture as well that's really important. It's buffering temperature and humidity. So this is my idea for a traditional thermal envelope. It's actually, okay, I'm using a bioaggregate that happens to have the right qualities for what I'm trying to do. But the traditional thermal envelope actually does this already if it was designed properly, but some things have gone wrong. Back to front, the EPC model. Or did I say the EPC model is back to front? And of course it's the Green Deal and all the rest of it, but let's have a look at the science that's being applied. So this is my neighbour's house. It's identical to mine, interestingly enough, and it's on the road behind, and it faces the opposite way. So where I've got a nice south-facing front facade, my neighbour has got a north-facing facade. So they've had wall insulation fitted to the back of the property. They've actually chosen to go with the breathable to make sure that moisture can escape out. Except moisture doesn't arrive on the inside of the back wall in order to get out. Because the wall is now insulated on the south side, it no longer captures any solar gain. It no longer gets any hygrothermal buffering. It doesn't actually capture any energy from moisture outside. And what it's done is it's made the north facade relatively colder because it's uninsulated. A couple of points that might be of interest later is that, I'm not quite sure how these details are being solved, but you've got things like drops in the terrace and this little bit round here, and also how you bring your sills forward, because sills are really important. As well as the fact that this being south-facing, what's interesting is that the bathroom on the back means that when you open the window, the air comes out, which is really good. The air comes this way through the house, so that's quite relevant too. But yeah, extending the sills out in like concrete would be terrible. Just up the road, here is a nice traditional Victorian terrace, and it's got a hygrothermal envelope. It's all beautifully intact because it's nice and south-facing, and actually it's not had too many problems. It's still got difficulties like drops in the terrace and such like, but it's hygrothermal. And to be honest, it doesn't need insulating. It's actually capturing not only solar gain, but it's actually capturing, on a warm day, it's a bit moist. On a cold day, it's a bit dry. So this hygrothermal thermal envelope is actually capturing energy. The best thing to do would be to insulate the north. However, of course, the north side's decorative, isn't it? So how can we do that internally? Here's a nice Victorian terrace with internal hygroscopic wall insulation. This is Yale's Victorian terrace, and it's a very, very interesting one as well because it also indicates where things have gone wrong, because although it's got this beautiful architectural detailing we all aspire to, actually all of these components you'll find in houses like this in Bristol are hollow. So these look like coin stones, but coin stones have a purpose, and these coin stones are hollow, which makes them cold. These columns are all hollow. Likewise the panelling under here, so all sorts of moisture problems. And then when the coal fire disappeared and the gas fire went in, the internal bathroom went in and the kitchen went open plan, this north facing facade got damp. and that's well, I think it's looking much better. But it's been done with hemp. So there's the hemp and lime going in on the inside. And now what we've done is we've taken away that storm. So whereas before we had discord, where instead of energy being lost everywhere in all direction according to the U value, X amount of energy goes up through the roof, X amount of energy goes up through the walls, through the windows. Now actually there's convection currents moving all that warm moist air from the warm source of moisture, such as the kitchen or the bathroom, and delivering it straight to the coldest point of the house. It's actually conveying your energy to that cold spot and out of the house. So that's the bit that really needs tackling. It's just that cold, damp corner in the back bedroom. So the hemp and lime tackles that. And it's also, I think this was done for, material-wise, about 700 quid, which is a lot less than other options. All right, Breathable. I'm sure everyone in the room is familiar with what Breathable is. This is my mountain jacket. It's breathable. So it allows the little tiny moisture vapor particles to actually go out through the tiny holes in the vapor permeable mountain jacket. However, it's got no capacity, unlike my woolen cardigan. I must admit the woolen cardigan is actually starting to lack a bit of capacity as well, but less said the better. So a natural material, whether it be brick, stone, wool, has got a hygroscopic capacity. It also has a couple of other characteristics, what I call velocity and polarity. So for example, if you think this cardigan is good, check out the velocity of my underwear. Because my merino wool underwear is a hygroscopic material, but it's got different characteristics because not all breathable materials are the same. So, vapor permeable. I normally got loads and loads of props, and I've got a few here, and we've got some hemp and stuff and things, but actually I can't carry all these bricks around with me all the time, especially as I came here on foot, even though I'm running out of shoe leather. So, the breathable materials, good example, Tyvek. It's just like that mountain jacket, but it's a synthetic material. It's got no capacity, but it's got the little tiny holes in it. We use that as roofing felt, and apparently that fixes everything. This is a loft insulation made from recycled plastic bottles. Great, fantastic, eco. Problem is, again, it's synthetic. It's got no capacity. So what happens is, when the this happened to you, didn't it, Ben? When the extractor falls off. In fact, Roger's not here, but his extractor fell off in his loft, and it just pumped moisture, and then it just got saturated, even though it's not hygroscopic. So again, problematic. This is a polyurethane foam board. It's got a fantastic U value because U values are all based on trapped air. Of course, making this stuff airtight is practically impossible. You need to learn how to use a foam gun. However, it's not breathable. Technically speaking, it is breathable. An aluminium balloon will deflate. The space shuttle actually needs, stuff putting in it. And of course, moisture isn't necessarily just coming from the inside to the out. The model's up and down, so moisture can actually come in from the outside. So on a frosty morning, it rains in my bedroom because I've got some kingspan on my ceiling, and as the sun comes around, it melts the frost on the back of it, and then it runs down. And because it's detailed so that, well, it's just a temporary measure, what happens is that the water runs down and then it basically comes into the house. And you see little damp patches occurring like that, and it's not a roof leak. Now this is a wood fibre board, so this is considered to be a really, really good option. This is what's put on the back of that previous property, and it's breathable, so that's good. But it also has a hygroscopic capacity, but I don't think it's got the right polarity. So we'll look at that in a bit more detail. And of course, this is natural materials. Now this is a hemp fleece. This is actually this flax fleece and all sorts of different types. They again have got different hygroscopic things. So it's breathable, but actually it's got some other characteristics we're going to look at. Because wood is more than just breathable, it's hygroscopic. Even though when we look at these skirting boards, it's really important they have a vapor control layer. But even this gloss paint will allow moisture through it, so it's breathable. This gloss paint is breathable, it's microporous, but actually it stops that peak of moisture from going through, protecting the skirting boards from woodworm. It's one of yours, that, isn't it? Right, so hygroscopic capacity, velocity and polarity. If you put a cake and a biscuit in a tin, do thank the firm for the biscuits, very nice. The cake dries out, and the biscuit, no, sorry, the cake dries out and the biscuit gets soggy because they're equalising moisture. It's kind of like osmosis, but actually osmosis requires a barrier, but they're just equalising moisture content. So when you're working with a hierarchy of hygroscopic materials, it's important to understand how they behave, but that's how moisture is passing. So they're passing as tiny, as a gas. So here's a nice hygroscopic material. It's called slate. Slate is hygroscopic. It's used as a damp-proof course because slate is a very, very closed stone. It actually, although it's got hygroscopic capacity and a huge capacity because of its mass, it actually moves very slowly. Therefore, it's got poor velocity. Oolitic limestone, which is what Bath is made from, and many of the properties around here, is a very, very open stone, it's got some very, very interesting characteristics. So we use it in particular places. In fact, there's different types of oolitic limestone that we use in different ways. So it's got really, really good. It's got a fast velocity. So it's got good capacity and fast velocity. This is hemp. Hemp has got something really interesting going on because you see, tropical timber is really, really good at breathing moisture in. It's not very good at breathing it out. The polarity is wrong for making windows. You use hardwood to make windows and it's tropical, they're going to rot. If you use a temperate timber, it's a bit of a rule of thumb, then it breathes in slowly and breathes out quickly, which is why cedar's great for making greenhouses. They've got a different hygroscopic polarity. I suspect that hemp, and when I first met it, I just kind of knew, not only does it have really, really good capacity, because it's got all this lime in there giving it mass, and as well as all this bioaggregate that gives it somewhere for all the moisture to diffuse to and then evaporate away from, it's got good velocity in both directions. It's omnidirectional. So if you want to make a condensation-proof bathroom, don't use sapele and don't use cedar because one's going to get very dry, the other one's going to get very wet. So hemp seems to be doing the job. Lime is breathable, but it isn't hygroscopic. It's what you put in the lime that's hygroscopic. So traditionally, when you mix a lime mortar, you're actually putting in like stone waste. So if you're working with a really, really open masonry like oolitic limestone, you would use the oolitic limestone waste, and then you've got calcitic aggregate that is going to make it a nice open mortar. You need to match that. Whereas when you're using like a closed stone, you might use a closed dust, and then you want them to match. Now this actually came out of a house in Bath, and I was particularly interested in the damp-proof course. It's Victorian, and they've used clinker. Well, it looks like clinker. We need to get that tested as a damp-proof course. Now clinker is like an ironstone. It comes out of fire, and it's but it's got no capacity because it probably has a bit, but it's very slow. So when I see Victorian property, what I see is the mortar being more mass-produced. Instead of being made on site with the local stone, all the rest of it, what you find is it's got these little black particles, and instead of being charcoal, which is something you'll find in mortar, which is hygroscopic, it's got clinker. The little black particles are clinker. And not only is it for the brick, actually you'll find the render on the inside is got clinker in it. So instead of the lime plaster having hygroscopic capacity that's got a good velocity, it's actually quite slow and closed, which might be appropriate outside, but it means they even start to fail right from when they were built. This is the model that kind of sums the whole thing up. I use these little bath time toy buckets. So if you can imagine that each one of these materials has got a capacity, like one of these buckets, bigger or smaller. And then what they've also got is holes that come in and out of them. So each material maybe allows moisture in at one rate, maybe something like the tropical timber, it's got big holes in and small holes out, whereas the temperate timber has got small holes in and big holes out. And so we've got something like hemp, which has got big holes in and big holes out. So it's a little visual trick for how I remember how all those work. Moisture buffering exteriors and interiors. So I mentioned before these different hierarchy of hygroscopic materials, and it's very, very important that we match the mortar to the masonry, because if the mortar is closed, then all the moisture gets taken in by the masonry, and then you get damage occur to the masonry. Inversely, if you've got an open mortar and a closed masonry, then the mortar gets damaged. So let's have a look at some real houses. This is some pennant stone, which is a sandstone, and it's fairly slow. It's kind of got iron in it, so it's a bit like the clinker. It's kind of it's quite close. That's okay. It means that it doesn't really get damp on the outside, and it kind of generally survives being, you know, the inappropriate mortars. Meanwhile, around the window detail here, we're using oolitic limestone, which is an open stone. Now, when you start building terraced housing, bay windows are really, really good. They're an aerofoil. As the wind passes down the street, it sucks the air out. So, meanwhile, on the inside, the facade, which is the bit that's always decorative, has got the windows, and the windows are pulling all the warm, moist air to the cold surface. So there's a convection current running around here. So we need to protect these details, because when we bring moisture to the window, you know, there's a risk that we might actually cause some damage. So what we've got is this nice open oolitic limestone, but it's also been cut in a particular hierarchy. So let me see, the head up here, that's the lintel across the top. The head has actually got the grain running that way. So that's the sedimentary layers, but it's been cut in the quarry and it runs that way. Over here, the jamb on the side, well, doesn't matter so much. You know, it's also got the grain running. It's got the grain running vertically, and you know which way around you have it. It's not load bearing. It doesn't really matter. Up here, it's sat like that so that it can actually cope with the load bearing capacity. In fact, let's move on to the load bearing capacity is transferred onto the abacus, which is got horizontal stratification there. Moisture can move through it more easily that way. The capitals, they're freestone, and they can allow moisture to move in all different directions. The jambs here, they're columns, so they actually need to have the stratification running that way, so they're much stronger. They're generally vapor checked on the inside because the windows will have some sort of detailing. So, and then down here, the sill. This is normally freestone again, so that moisture can move as all that warm moist air reaches the bottom of the window here. This sill is really important, and we've done a lot of repairs on those with the hemp underneath the windows on the inside, because that's where the moisture drops out. That's where it's being fed through the building. And you'll often see decorative panels under windows, because again they've got this high surface area and can take moisture away. So here's a modern building. This has just been built. This is Lucas's school, Pete. So the council just built a new school in Bristol, and I was just saw this the other day. They've put a nice breathable, eco-friendly lime render on it. I mean, it's a concrete block building, so I don't know why. Well, of course it doesn't matter because the moisture goes through, so it's all right, isn't it? It just keeps drying. However, when the moist air comes down over this building and it starts to fall as it reaches the thermal mass and cools down, it drops down here, and this bell cast should actually be at least 6 inches off the ground, because that's a drip edge, isn't it? Now the bell cast is there to actually kick the moisture out. It's a plinth, so this is getting saturated, and the reason being is that this is really breathable. It's like oolitic limestone. It's really fast moving. It's responding, but the concrete paver is concrete. It's closed. The aluminium window detailing, well, that's all closed. So as the warm moist air arrives here, this is going to be absolutely shot. It's going to get saturated. It's going to fail. It's going to end up looking like that. Mm-hmm. And lots of modern architecture is emulating. Oh, this is in a conservation area, so it's got parapet walls but you know, I mean, this is just where the water detail. I see loads of this stuff, and I've got thousands of photos of stuff that I'd love to run through sometime. But so that damp problem on the outside is causing evaporation unnecessarily. That's causing heat loss. So what you get with a broken gutter on the outside of a house is a cold spot. Now that cold spot attracts the internal weather to go and meet it, because if that keeps evaporating away, you're getting latent heat loss. So here's a damp problem with a broken gutter on the outside, and if anybody would like to come along on a workshop, we're going to have a little site visit on Saturday. I've got a couple of people coming, if anyone else wants to come, and we're going to have a look at the Hemp-lime, and I'm proposing to fix this gutter leak without fixing the gutter, because I'm going to just fix the internal weather and leave the outside to cope. Just for fun. Because if we find a cold spot in a house and we just deal with that, you know, having all this really invasive work, you know, and I just want to sort this damp problem out in the corner, and that's where all the heat's being lost. There's something going on that's caused that to be the corner, because the local topography, the local weather, the local solar aspect. Consequently, just tackling that cold spot can be a great energy saver, because it means you can turn the heating down, put a jumper on, and live in a different way. So this is a hygrothermal cornice. It's not decorative, it actually has a purpose. It's actually breaking up the air current, just like that bell cast is supposed to be doing, to stop moisture collecting in the corner. Sorry, that's a Hemp-lime ceiling. Here's another Hemp-lime ceiling. So you see what's happening with this air is so just like at the bottom, the warm air rises to the top, and then we've taken the corner out with by curving it, and then we've done an inline moulding. It's not decorative; it's there as a beak to create turbulence. You see this on the outside as well, so it breaks up the air. And of course, wallpaper. Wallpaper is really, really important. Wallpaper is kind of like the bit in between. You see, the wallpaper is really, really quick to respond to the moisture content in the room. But it's got really small capacity because it's quite thin, so it can diffuse it to the lime. Then the lime takes it to the hemp, and the hemp takes it to the brick. So each one of these materials is actually working with each other to keep the moisture content down. Right at the bottom of the room here, we've got the plinth. And the plinth is vapor checked, it's got gloss paint on it, little detail. You always scribe your skirting boards because they need to expand and contract. The gloss paint is a vapor barrier. So you see, detailing timber is about not trapping end grain, allowing it to move properly. Right, architectural detailing. I'm going to run through this fairly quick because this is a dialogue. This is what I really want us to have a conversation about. So I've got some functions that I can apply to some different detail. Architrave, abacus, capital, column and plinth, what we just ran through. And also some facades. We've got aspiration, emulation and remediation. We've also got the process, the difference between contractors and journeymen. So, first of all, columns. So, these columns are fluted. As the wind passes this way across the building, they're actually wicking moisture away because they're creating low pressure. They're also protecting, they're giving massive thermal mass to the building, but also the evaporation that happens at the tip where it gets wet, well, that's not going to cause a heat loss issue. Meanwhile, there's banding that's creating, protecting things like the floor joists and such like. So you'll find the architraves, all these different things are actually helping to protect the internal structure, lintels and such like. So we've looked at open and closed stone, which is what's really important with getting the mortar right. We've also looked at the hierarchy of materials. Now we're looking at how those materials are put together in a way that solves problems. So where it's thinner here, moisture can get out through the building. There's a nice niche, nice alcove that actually, as the wind passes over here, it's actually pulling moisture out. So although there's no window on this side of the building, there is an opportunity to pull moisture out of this building. There's an area that's not going to be susceptible. And you'll see this decorative panel where you've got a thinner section. You find that often is put on modern buildings as well, this decorative panel. Now, this is vermiculation, and it's impossible for moisture to actually get in there. The rain can't get in. It's really important that this creates evaporation for rain, but also it's always possible to get moisture vapor out because it's always dry. So detailing like this is really, really good. So is pebble dashing, because although this is a closed stone, the stone is maybe closed, but it also means that it can massively put a big surface area on things and actually create evaporation. That needs to be considered when we're refurbishing this building. Got those details under the window, losing moisture. But we've also got hidden detailing. You see, because of that hierarchy, you'll find that this rendered building is, this will be like yours, Ben, actually. This is, can't see this, but you've got this more open stone around the windows to cope with the moisture around here. And also this panel, it's all rendered over. Really importantly is that oolitic limestone sill. That's the one that's actually pulling the moisture out of the dew point on the inside. Here's an architectural detail that really I find fascinating. When I look at those columns and how all those horizontal and vertical details can help deal with rainwater and moisture coming out of a building, I see shop fronts. This is an unusual one. What you've got here is a lintel. It's a really, really big, challenging thing that the client wants, and I'm trying to sort a few things out here. So we've put in ways of mitigating problems with damp and stuff with corbels and such, which shift the dew points. However, you'll find some buildings have got ceramic, which makes no sense whatsoever. And yet, it's always buildings you want to keep cool. It's always chemists, butchers and pubs. Pubs will be rammed like now. I had to turn the heating off when I arrived at 5 o'clock. knowing you were all coming. You'll often see there's open vents up here because this will be constantly vented. It doesn't want to capture any energy. So there's a history of stuff here. There we go. So we all aspire to those wonderful facades and aspirations, but actually what we get sold is this, because there's a difference between a contractor and a craftsman. What we're doing is doing stuff like this, and our energy retrofitting is going to destroy properties because it's not very well thought through. You can see there's a history here of damp remediation, but actually there's an occupant behaviour going on, as well as the landlord keeps trying to damp proof the outside. Here's a nice interesting landlord property. It's got water pouring down the north facade. They've just spent God knows how much putting a new roof on this place, new chimneys, everything to stop the water getting in. Actually, the coping stones on the top face the wrong way. The person that put them on didn't know what they were doing, and no one ever since has actually pointed this out. Now, this is also northwest facing, and it's a property that's been converted to flats. So there's 4 flats in this building. Each one's got an internal bathroom, an internal kitchen, no outdoor laundry space, because the bathrooms are on the north facade, the bathrooms and the kitchens are on the north side, these drafty sash windows are actually sucking air in, which is great, isn't it? I'm ventilating my bathroom. No, if you drop the sash windows up and down and close the door, then you'll change the air to the room. But actually all it does is it pulls the warm, moist air from the bathroom into the rest of the building. There's a conflict going on here. Beautiful original tiling, new concrete tiling. There's an energy and damp problem going on in this property. Normally you see this after the chimney rendered as well. You see the parapet's been rendered, they've put new copings on, every person that's come around to try and fix this damp problem has ended up selling a new roof. And yet next door, if anyone can tell me, I'll buy you a pint if you can tell me where that chimney pot is in Bristol, because it's one of my favourites. And as to what it's doing, well, because actually what it's doing is it's stopping the prevailing wind drawing the chimney unless it's lit, so you don't get air loss. You see, that's what the Queen and the King do. You see, the air goes under there and it goes that way. What you do is, and this is brilliant. Like that. Can anyone see what's causing the damp problem in this house?
The capped chimney.
The gas cowl. There's a history here. Right. There is a difference between a contractor and a journeyman. So I was at Wells Cathedral in September with the Building Lines Forum, and I'd love to tell you all about how they spent 40 years preserving these statues, which are in niches that get massive evaporation. So this west-facing facade that really gets it, it's got all this amazing detailing to actually protect it. And these statues are like columns. They're there to kind of protect the building, create evaporation, and the air can whip behind them, and it protects the structure behind. But there's also a hierarchy here of trained masons. Down at the bottom, right down here, there's here we go, in these little niches. As a journeyman, you would turn up, you display your work in there. None of these pieces are fixed. That's where you display your work. And up here, this guy just died recently. The guy that rebuilt that statue, he died just this last year. So you see, there's a whole sort of training and a hierarchy of knowledge there. While I was there, I met George O'Malley. George O'Malley is from Ireland, and he would consider himself a plasterer. And he repaired St Giles Cathedral. In the middle of winter, at sub-zero temperatures, this cathedral set on fire. And this plasterer fixed it. Now, I said to George, I said, that's hygrothermal passive heat recovery. He said, yeah. Because this isn't decorative, this actually serves a purpose. It's actually, all of this decoration, all this detailing is actually capturing energy and damp. And the key thing, because the frequently asked question that I get with my idea on architectural detailing and that there is actually a purpose for everything. Of course, some of it's been emulated, some of it's gone wrong, and there's been a problem with knowledge transfer. In the trades, this stuff isn't written down, it's passed down through generations. When you start out in the trade, you just learn to cut stone. You might just stay as a quarryman cutting stone according to what you're told. But some people become master craftsmen, they learn everything. And it's only when you start getting a few grey hairs that you can look back and realise that Yeah, I remember that job. Yeah, we got called back on that, didn't we? Yeah, because we had a bright idea, didn't we? Yeah, actually, yeah. So there's a whole kind of set of reasons why you do things, and I would refer to it as reputation and liability. Okay. It's about the difference between what the client wants and what the client needs, and sometimes you've got to use a little bit of Jedi mind tricks to get to make sure that your reputation stays intact and your liability. So, to finally indulge myself, we've got these things called unintended consequences, and this is what I would love to have a conversation with you after we've taken a bar break. And it kind of looks like this. It's the no cost and low cost joined up thinking. I'm building a board game. It's a sort of a way of finding your way around eco-renovation. It's quite fun as well. There are 4 sides to this board game. You've got occupant behaviour, draft proofing, insulating, and damp remediation. What's really important is that occupant behaviour, you can't just say behaviour change. That'll close your doors, that'll fix it. You've actually got to do some informed occupant behaviour. You need to inform people how to do it. Likewise with draft proofing, you actually need to know how to be successful, not just stick products. Like that's what contractors are doing. So a contractor just follows a spec. If everyone is actually all together trying to achieve the same thing, then we can actually, we could build a St Miles Cathedral. But we don't do that we don't have that kind of knowledge in the retrofitting market. Because if you're actually going to teach someone to do occupant behaviour to change their home, they don't need wall insulation, they don't need damp remediation, they don't need concrete render, they need to learn to close their doors. But you cannot tell them. They have to want to. Self-determination. Self-determination is about choosing to, not being told to. Autonomy, achievable goals, putting in place if-then strategies. The board game will help with that. Likewise, successful draft proofing. When has any draft proofing workshop ever suggested that wind sucks and that you need to understand cross ventilation, stratification, convection, and that if you start with the large holes, you identify the small ones. It's really easy. And if you're not Universal, you could spend a fortune on this product. It makes no difference. That's okay as long as you understand that. You know that you're dealing with this now, but that's for later, and so on. The principles that I'm applying to the board game actually tell you the things that you need to know. And this can be shared between, on one end of the spectrum, you've got your contractors, on the other end of the spectrum, you've got DIY. Because if we all need to move forward together, and we can fill the gaps in with a bit of joined up thinking, if actually the DIY person can, well, I'll deal with that bit, but we're all trying to achieve the same thing. And your contractor knows when they're putting the foam in, there are principles that need to be understood. Damp remediation. Okay. Informed, successful, and strategic. Mitigated. That's me done.